Hello everyone, my name is Gay Yee Hill and welcome to this NASA Science Chat on Dawn. I am sitting in the control room, mission control of JPL, which is home of the DSN. And right now, I don't know if you can actually see it on the screen, but the DSN is talking to the Dawn spacecraft right now on the Goldstone antenna, like it has for the past 11 years. It calls home every week. Well, the situation is going to change after a while because the spacecraft is running out of fuel, which actually affects its orientation so that it no longer can point to Earth and talk to us. So that means the mission is coming to an end soon. And we thought that this might be a great opportunity to talk to you and have you talk to us about some of the great things this mission has accomplished. Let's take a look back. I have some animation for you and we can look at what this mission has done. It started in 2007, it launched that year, and it was a mission to the main asteroid belt. It was headed for the two largest bodies in the asteroid belt, Vesta and Ceres. And the reason why they were going there was because these two places are sort of like time capsules of the early solar system. Now, this is your opportunity to ask us questions. So if you're a reporter and you're dialed in, hit *1 when you're ready to ask a question. And if you're on social media, go ahead and use the hashtag #AskNASA, and we'll put your question in the queue. All right, let's take a moment now and get some perspective. Before dawn, this was the only image we had of Vesta. It was an image given to us by the Hubble Space Telescope. And then post-dawn, after dawn arrived, we get a much better image and a better understanding after this spacecraft mapped and orbited this body. Same goes for Ceres. Ceres, again, the only image we had was from the Hubble Space Telescope, just a fuzzy ball. And again, post-dawn, you see a whole lot more. So it's your opportunity to ask questions. Please do use the hashtag #AskNASA. And now let's go ahead and do an overview of this mission to small worlds.
You know, when you work on a mission this long, it feels like a part of you. I've been a space enthusiast since I was 4 years old. Getting to work on a mission like this it's a dream come true. To me, Dawn is truly Earth's first interplanetary spaceship. No other spacecraft has gone to a distant body, gone into orbit around it, maneuvered there, then broken out of orbit, traveled elsewhere in the solar system to another alien world, and gone into orbit around it. And it does that with ion propulsion, which I first heard of in a Star Trek episode. We've turned ion propulsion from science fiction into science fact.
The Dawn mission really is a journey back to the beginning of the solar system, and that's why we call it Dawn. We chose two time capsules from the beginning of the solar system, Vesta and Ceres, which are the most massive and largest bodies in the main asteroid belt. They both formed very early when the solar system was forming out of the protoplanetary disk, and yet they ended up in these two very different states. Vesta is a dry, rocky body that looks a lot like our moon, whereas Ceres had a lot of water and it looks much more like the icy moons of the outer solar system.
And it seems like what determined their eventual fate was the location where they started. And we now believe that Ceres formed much farther from the sun than it is now.
When Dawn found the bright material on Ceres, what we saw was completely mind-blowing. It was made of sodium carbonate. Sodium carbonate is not common in the solar system, but we see it coming out of the plumes of Enceladus. We see it in lakes on Earth, and here it was on the surface of Ceres.
The mission will end when Dawn runs out of the conventional chemical propellant that it uses to orient itself in the zero gravity of space. Dawn will become this inert celestial monument in orbit around the dwarf planet that it unveiled. Dawn serves as a lasting reminder that the passion for bold adventures and our noble aspirations to reach out into the cosmos take us far, far beyond the confines of our humble home here on planet Earth.
All right, so we know you're anxious to speak to our panel, so let me introduce them. Let's start here at JPL. Carol Raymond is the principal investigator for Dawn. And then next to her is Marc Rayman, different spelling, and he is the mission director as well as the chief engineer. And then let's jump over to NASA headquarters. There's Jim Green, and he is the chief scientist for NASA. Jim, let's go ahead and start with you. Tell us why NASA decided to have this mission go to the main asteroid belt.
Well, you know, the asteroid belt is a very unique area that surrounds our sun between Mars and Jupiter. It has hundreds of thousands of objects that we know about, and perhaps more than 1 million that are out there, many yet to be found. But what's really unique about this particular area is that it's really all about planetesimal material, small planetoid material, trying to become a planet, trying to get together. But it's failed. And the reason why it's failed is because of Jupiter. Jupiter's gravity is so immense, and it pervades the asteroid belt, that as objects collide and then try to become one, and in a process we call accretion, Jupiter's gravity won't let that happen, kind of tugs them apart. This is what's kept this region to be very primitive. Now, for Dawn, Dawn is not an acronym. It's really going to the beginning of our solar system, the dawn of our solar system, which is one of the reasons why I really like the name, and then interrogate two of the biggest bodies that are there. You can't get much better than that.
All right, thanks, Jim. So the two bodies are Vesta and Ceres. And let's bring it over to Marc Rayman. How did we get there?
Well, we took advantage of ion propulsion, which I mentioned in the video I first heard of in a Star Trek episode. And ion propulsion has 10 times the efficiency of conventional chemical propulsion. And that's really the key to what allows us to undertake a truly uniquely ambitious mission. This would be like having your car get 300 miles per gallon. And without it, this mission would be not just difficult, but impossible, truly impossible.
So how does it work compared to what we're used to?
Well, again, it's just fantastically efficient, and we could get into the details later, perhaps of how it works. But one of the interesting aspects of it is, although it's very efficient, we only flow a very small amount of propellant through the engine at a time. And so it's very efficient, but it's very gentle. And in fact, the ion engine pushes on the spacecraft as hard as this single piece of paper pushes on my hand. And I think we even have an animation showing the use of this remarkable system going into orbit around Ceres. It really does produce this cool blue glow like in science fiction movies. And you can see here how maneuverable it is. And with this very gentle thrust in the zero gravity, frictionless conditions of space, gradually the effect can build up. So it would take Dawn 4 days to accelerate from 0 to 60 miles per hour, which doesn't exactly make you think of a drag racer. But instead of thrusting for 4 days, if you thrust for a week, or a month, or a year, or as Dawn now has for nearly 6 years, you can achieve fantastically high velocity. In Dawn's case, more than 25,700 miles per hour. So this is what I like to think of as acceleration with patience.
So it means you can go to a whole lot more places, I would imagine.
It opens up destinations in the solar system that NASA would otherwise be completely unable to reach. And it allowed us not only to get to both Vesta and Ceres, but orbit them, linger there for long periods of time, make detailed, comprehensive investigations, really scrutinize them and develop intimate, richly detailed portraits. And that's what has produced the fabulous scientific return that we have.
And speaking of the scientific return, let's go to Carol now. I think a lot of people know that these are two bodies in the main asteroid belt, but they have no idea what they're like, what they are. One is a dwarf planet, the other is not. Can you explain these two bodies?
Sure. I think the important thing to realize about these two bodies is, as was said in the video, and Jim also repeated, these are time capsules from the very beginning of the solar system. And what we're after with the Dawn mission is to understand what the conditions were like in the early solar nebula when the bodies started to accrete out of the protoplanetary disk. And as these bodies accreted, they incorporated the material that was native to their neighborhoods, and then they kept accreting into bigger and bigger bodies. But these earliest blocks tell us an enormous amount about the processes and the materials that were available. And so we want to answer questions of how and when did these bodies form, and then how did that material move around in the solar system as the planets were forming. And we're actually trying to get at big questions like how and when did life arise, and then was it distributed within our solar system by these small bodies that may have incorporated life within them. So Ceres and Vesta are these two intact survivors from this era, and they're very different objects. So they represent two chapters, we could say, in solar system history. And Vesta is a good example of the inner solar system. Vesta on the right, it's a dry, rocky body. It underwent melting and formed a core, kind of like the Earth, Mars, and the Moon. Whereas Ceres, the large dwarf planet, 1,000 kilometers in diameter, this is really a small world, and it formed with much more water, still retaining a lot of water. And the processes that went on inside of Ceres are very, very different than Vesta. So by understanding how these two bodies formed and evolved, we're getting a picture of the development of other bodies in the solar system at that earliest epoch.
And how bodies like Earth formed.
And those bodies came together to form the Earth. And so it also tells us about the materials that were available to form the Earth and other planets.
And Mark, you wanted to add something?
I was just going to add a little context for the size of Ceres, that 1,000 kilometers, that's almost 600 miles across. This is a big place. And Vesta has an average diameter of 325 miles. They're large.
All three of you have set a fantastic stage for our questions. Again, if you are a reporter, feel free to hit *1 and you will be placed into the queue for your question. And if you are on social media and you also have a question, go ahead and use the hashtag #AskNASA. And we have some questions already. Let's get started. The first one is from James Moore, and here's the question. Biggest difference, if any, between Vesta and Ceres, and the biggest surprise in exploring these two? Who wants to get started? Go ahead. Yeah.
I'll be happy to.
Oh, all right. Jim, take it away.
Yeah, I mean, to me, as a planetary scientist, but also not a specialist in these bodies, this is almost like night and day. I mean, the concept that you had much more of an icy set of materials that formed Ceres wasn't the environment that we had for Vesta, as we just talked about. And that Vesta was big enough that it indeed early on in its history melted the material and created a core. This is the basic process of differentiation. This is what we call then the development of the beginning of planets. So it's like what we'd call a planetesimal, a small body that's starting that whole process. You get a whole collection of these together and you form things like the Earth. But their contrast from one mission alone is just, to me, so startling.
Carol, do you have something to add?
Well, I would say that the biggest difference is clearly the interior and the chemistry, as Jim has already talked about. But also the fact that we now understand that Ceres must have formed much farther out in the solar system. It's more like bodies in the Kuiper Belt, in the trans-Neptunian region, so that it was transported in during a dynamic reorganization in the early solar system. So it's even more compelling because it represents a class of objects that's very hard to get to with spacecraft. And then we have Vesta that's much more like the terrestrial planets, and so we learn so much from learning about how this early forming planetesimal formed and evolved.
Which was so amazing about this mission. It was a twofer.
It was, and in fact, I was going to say their superficially similar distances from the sun really belie the fact that they're very, very different. I mean, the premise of the question was, you know, maybe they're similar, but what are some of the key differences? But really, they're different in myriad ways.
All right. Well, we have a reporter on the line. We have Dave Mosier with Business Insider. Dave, what's your question?
Thanks for doing this. Really appreciate it. I guess this is for anyone who takes it, wants to take it.
Okay.
So a couple questions. Do you have an exact date or approximate date for when the mission will end? And then a follow-up to that, why is the cutoff 20 years, and what is sort of the planetary protection explanation for that? Is that when sort of enough of the microbes that might be left on there are croaked, or is that something of an arbitrary designation?
Okay, so the first part of the question was, I do have an exact date for when the mission will end, 2018. More to the point, we can't predict it with perfect accuracy because the spacecraft relies on hydrazine propellant, which we use to control its orientation in space. That is, it doesn't have anything to do with where it goes, but how we orient it.
Okay.
And when it exhausts this propellant, it will no longer be able to point its solar arrays at the sun, or its antenna at Earth, or its sensors at Ceres. And we can estimate that will happen most likely between the middle of this month and the middle of October. But for various technical reasons we could get into if we wanted to, perhaps afterwards, we can't determine that with exquisite accuracy. And so the spacecraft will operate normally until it exhausts this propellant, and then it will no longer be able to control its orientation, and it won't be able to communicate with us.
All right. We're going to move on right now to another focus area, and that is Ceres. That's where Dawn is right now. And one of the most compelling things about being at Ceres are these bright spots that we saw as we were coming into Ceres. And here's a video we call The Bright Stuff.
Approaching Ceres, we saw this very bright region on the surface. And then as we got closer and closer, you saw that there were multiple bright regions in this one crater.
What we're seeing is an indication that there are liquid brines, potentially in the subsurface, even in the present day, rising to the surface and becoming these bright spots. And that tells us that there has to be a process providing energy to drive these fluids to the surface. We call them bright spots, but actually it's a relative term. The brightest bright spot on Ceres has an albedo of around 0.5, which is about the same brightness as dirty snow. We found that there are over 300 bright spots all over the surface of Ceres, and that indicates that this is a relatively widespread process.
The salts that we see in Okato crater are similar composition to salts that we find in Mono Lake in California.
Ceres represents something of a bridge between the bodies of the inner solar system and the outer solar system. In the inner solar system, we see rocky bodies. In the outer solar system, we more broadly see icy bodies. And Ceres is sitting somewhere in between. We know now from the bright spots that it is changing. The bright spots that are already on the surface are darkening over timescales of hundreds of millions of years or even less. And we also see that the bright spots maybe are still forming. So Ceres is still an active body. And we still have a lot of questions about what are the processes that are modifying Ceres' surface over time, and what that tells us about the internal nature of Ceres and how it actually formed.
All right, the subject matter is Ceres and the bright spots. And the intriguing thing that you heard in that video is still active. Things are still going on. Can you talk about that?
Sure. This was one of the biggest surprises at Ceres, was that we found features that clearly are very young. We know that from the brightness of the features, the types of materials, and the fact that they degrade over time, as Nathan was talking about, but also these very young looking shapes, morphology. And one of the real postcards for our Ceres activity is Ahuna Mons. It is, Mons means mountain in planetary nomenclature, and so this is a lonely mountain. It's the only one on the surface of Ceres. I think we have a picture of it, yeah. And you can see that the slopes are very steep, and you can see that that bright material, which we know now is sodium carbonate with ammonium chloride salts, is streaking down the sides. It's actually starting to degrade and to become flatter, really, over time. So we know that this feature is very young, and we believe that it formed because there are pockets of brine in the subsurface left over from the phase when we had a global subsurface ocean. And so these briny, salty fluids are being squeezed up, likely due to the pressure of some freezing material in the subsurface, and they're extruding on the surface and forming this beautiful mountainous feature.
It is gorgeous.
13,000 feet high. I mean, this is an impressive structure.
And it's the only one on the entire surface.
Right, and so what the thinking is that it's not the only one that's ever existed, but it's the one that we see today preserved because it's so young. Wow. So over time, these features will basically relax and degrade, and they'll become much flatter. So you can think about it like erosion on the Earth, but erosion doesn't take place on Ceres, but there are processes which will degrade features over time. So we think that this one is just very, very young.
You can think of it just as if you pinch your skin. After a while, it relaxes back to its original shape, and the same processes occur on Ceres, same kind of processes, where over time these features flatten out and eventually disappear.
All right, well, we have a caller on the line, Mike Wall with Space.com. Mike, what's your question?
Thank you, guys, for actually doing this, first of all. And yeah, I mean, I apologize if this question is like a little redundant, but I actually had to hop in a little late. Could you just, just kind of walk through, Mark, what's the long-term sort of fate of Dawn? I mean, it's going to stay in orbit around Ceres for a number of years after the fuel runs out, right? Do you have an idea of how long that's going to be, and when it's going to eventually spiral down and actually crash under the surface?
Okay, well, were the listeners able to hear that question as well?
Yes.
Okay. So the reason first of all, let me remind you of the reason we're leaving it in orbit. In fact, this relates to the question that came in earlier. We're leaving it in orbit to protect Ceres from the terrestrial contamination of Dawn. And it's not because of the microbes that were asked about earlier. There are microbes that are hardy enough to last far, far longer than the few decades that we're concerned about. Rather, it's because with its combination of organic materials, water, other chemicals, internal heat, Ceres represents a place in the solar system that we're interested in for future astrobiological exploration. And the idea of leaving it in orbit for at least 20 years, which is the requirement, is that that's long enough that if NASA chooses to mount a follow-on mission to conduct subsequent astrobiological exploration, it's long enough to do that without it being compromised by Dawn. And so in answer to your question, Mike, we are required to guarantee that the spacecraft will remain in orbit for at least 20 years, and that was part of the basis upon which we chose the orbit that it's in now. But our analyses give us very high confidence, greater than 99%, that it will stay in orbit for even half a century, and most likely longer than that.
And Jim, do you have any response to that as well?
Indeed, Mark's exactly right. The concept that we found of the body still being active allows us the exciting possibility of going back and studying it further. You know, if the Ceres was more like the moon, then we wouldn't be so particular about finding a way to keep Ceres more pristine. And so consequently, The body is so intriguing in so many ways, we just absolutely got to go back. This is a dwarf planet. It is maintaining a spherical shape. The gravity is allowing the motion of the surfaces with other processes going on, and that's evolving. The material that we see sometimes on the surface can be actually fairly young, tens of millions of years old. And so there's upwellings, there's kind of processes that we just don't understand, and that's what's drawing us back. And so we want to study those in their natural form.
All right. Well, we have a social media question now. This is from Don Sparrow. His question is, does the composition of Ceres and Vesta vary much from Earth or the Moon?
Yes, it does. Vesta actually has a lot of affinity or similarities to the Moon. It's a dry, rocky, basaltic crust, has basaltic crust on the surface, has an iron core. The density is similar to the terrestrial planets. So yes, the Moon has a core. The Moon has basalts on the surface. So it is similar in that sense. But Ceres is a completely different object, and it was interesting that we knew there was a lot of ice on Ceres, and we knew that it had been liberated from the rock and formed we predicted it had formed a subsurface ocean, and we expected to see that ice covering the surface like we see on Jupiter's moon Europa. But instead we got to Ceres and we saw this very heavily cratered surface, which made us scratch our heads a little bit. Did this process really happen? What are we looking at? And it took a while to realize that the surface of Ceres is a mixture of clays, salts, and ice, and a very light, strong phase, which is keeping it kind of as that, looking like a crust and being able to retain its craters. And that light phase is a clathrate. It's a gas hydrate. And
it's low density but very strong.
Yeah. So we could not really have imagined what the surface of Ceres was, that it would look like this. Yet the chemistry and the materials that make up Ceres are very, very different from the Moon.
All right. Well, we're going to move on to the next topic, but just before, let's do one more call. It is from Ken Kramer with what was the Space Up Close is the publication. Ken?
Thank you. Thanks for doing this. It's a pleasure to be part of this as well as since the launch. My question really is for all three, and it does pertain to the bright spots. I'd like to know, can one of you review what do we know about subsurface oceans or lakes at Ceres in the past and the present? And second, to go back to the follow-on mission, would you consider, what would you do? Would it be a sample return mission possibly to the sodium carbonate or Hunamans or elsewhere? Thank you.
Ooh, some loaded questions there. So what do we know about the activity? The gravity and topography have allowed, that we've mapped on Ceres, have allowed us to infer the properties of the interior, and the chemistry of the surface tells us a tremendous amount about the process of the ice melting, the interaction between the water and the rock, creating these salts and ice. And now we're seeing those salts, the sodium carbonates, aluminum chloride, on the surface of Ceres. How did they get there? We see them in these very specific young deposits. So we know that there is a process that's mobilizing those materials in the subsurface and bringing them up. So there has to be some liquids still inside of Ceres, some briny fluids, likely very deep where it gets a little bit warmer. And then the action of likely impact heat is causing those fluids to further melt and get driven to the surface. So we, as Jim talked about before, we know there is an active geological cycle that's bringing material from deep up to the surface, and that gives us an opportunity to sample that some of the Ceres' interior material by sending a mission to the surface. The holy grail of any planetary science is sample return. We all know that. It's also very difficult, and to an object like Ceres, you really want to know where to sample. There's so many different interesting materials that I think the next step has to be to explore the surface before we get to the sample.
All right. Well, we are trying to cover an awful lot of territory because the mission did so much. And let's not ignore the other place that Dawn went to, which was Vesta. And so here's a short video that show you some of the greatest hits there. So there you have it. That is Vesta. And what's so interesting about it is it's so similar. It has a core. It has, it has so many things that are so similar to the rocky planets.
Yeah.
And
things that are familiar to us.
Right.
Because it's similar to the Earth and the Moon. But the other reason we know Vesta very well is that pieces of it have been falling on the Earth. A tremendous amount of material from Vesta has been falling on the Earth for a long time. So there's a certain class of meteorites called the Howardite, Eucrite, Diogenite series that constitute about 6% of the meteorites that fall to the Earth. And that's more than the Moon and Mars combined. So here is one of the pieces of Vesta that's fallen to the Earth. This is a piece of the Milbalilli Eucrite. It fell in Australia. And its properties of these meteorites have been studied in laboratories for decades. And it was recognized as far back as 1969 that the reflected light from Vesta looked very much like the measurements of the spectra of these meteorites in the lab.
sort of like a fingerprint.
Like a fingerprint. And so that begged the question, did all of this material actually come from Vesta? And the answer that Dawn provided was yes. We believe that the HED meteorites all could come from Vesta, and therefore we have executed the first reverse sample return mission. We studied the samples, and then we went and looked at where they came from. And so this has made Vesta an even more interesting object. And just one more thing about that is that we don't know of any other body in the solar system that really matches these meteorites like Vesta does. So that means that even though there's a couple that look similar, Vesta is a singular, unique body in our solar system. So again, we're learning a lot about the diversity and about the early evolution by being able to study this body in the laboratory and out in space.
And we actually have far more material in our laboratories from Vesta, thanks to these meteorites, than we do even from the Moon with the more than 840 pounds of material Apollo astronauts brought back.
So you're kind of ahead of the game because you have samples right here.
Exactly. And the science community has been studying these rocks in every manner possible. So it does highlight how important it is to link space exploration with our robotic emissaries, with the painstakingly detailed work that occurs in the laboratories to really understand the chemistry and the processes which are captured there.
All right. Well, we have a social media question.
That's a fantastic.
Oh, I'm sorry, Jim. Go ahead.
Oh, that's all right. Well, I just have to say that section of a meteorite is spectacular. Look how large that is, and the uniformity of it, and then the details that we can tease out. I mean, the concept that we can actually relate those pieces of rock that fall from the sky with real objects is the start of I think, a lot more that we want to do, relating these pieces as we go back out to the asteroid or to other asteroids. It's just really spectacular. Dawn has been that first spacecraft that's allowed us to make that connection. You know, we have teams of people that go down to the Antarctic every summer to be able, in snowmobiles, crossing the snows, looking for falls, fresh falls, also looking for meteorites that have been on the ice shelf for long periods of time that have now surfaced. We bring 600 to 900 of them back every season, cull through them, and we only understand a small fraction of them. And so it's these kind of things that are just spectacular progress that we're making. Dawn has just made a wonderful connection for us.
Well, this question might be a little repetitious, but maybe you can give your personal nugget on this. What's the importance of understanding Vesta?
Well, Vesta also represents one of the very earliest forming bodies in our solar system. We can trace it back to the first solids that were condensing that contained a lot of this short-lived radioactive material, aluminum-26. And we know, because of the size of Vesta and the fact that it melted completely, we can peg when it formed to be between 1 and 1.5 million years after the first grains were forming out of our solar nebula.
Which was a little more than 4.56 billion years ago.
So Vesta, we have our bronze model here, is really such a time capsule, and is telling us about the fact that this body could come together very, very quickly. And we learned from looking at the pattern of the craters that hit Vesta, because it's been around for a very long time, in the middle of our solar system. We could find out that the other planetesimals forming at that time likely grew also very quickly because of the number and the size of the craters on Vesta. So we've learned not only how quickly and how the kind of evolution that Vesta underwent at that very earliest time, but we're also able to understand the bigger picture of how these objects were kind of like popping up out of the nebula and growing very big, very fast.
All right. Well, we're going to go on to another section, but before that, let's take a phone call from Dave Mosier and Business Insider. Dave?
Thanks again for doing this. Just wanted to follow up on the sample return mission question. What would that mission look like? Would the primary goal be to look into the geology or the astrobiological signs, either past or present, or would you try to do both at the same time? And then a quick follow-up to that would be, could that same mission also determine whether or not there is a subsurface ocean? Thank you.
All right. Well, we're going to lop that over to you, Jim.
Well, indeed, many months ago, we started to form a group of scientists to really be able to tease the architecture of a new mission out. This is so important for us to do so that we can determine how we would make major progress, the questions we would answer, the type of instruments that we would take that would enable us to probe below the surface, that would enable us to make specific measurements in great detail of the variations of the surface material and the salts. And then how are we going to get there? You know, how do we land? You know, one of the reasons that's really important to recognize that Dawn is in such a highly elliptical orbit is it has the ability then to give us high resolution imaging. This is absolutely essential as a way for us in the future to be able to leverage that data such that we can land safely. So those things that are all coming together, the science team has been talking about this and meeting. They're trying to construct the best way to go. And we'll get the results probably in another 9 months or so. And then that'll feed into a larger process as more studies are being done, and we'll work in the next we'll work out the next decade and whether one of those missions would indeed be going back to Ceres.
All right, we have still another phone question. This is from Leo Enright from the Irish Times. Leo.
Thanks very much. Irish television.
I thought that was wrong. Okay. Hi, Leo.
Indeed, and great to see a young Irish researcher, Jennifer Scully, on this briefing. It's great to see her contributing. But my question, going back to the comment about Vesta and how cratered it is, I'm wondering how come Ceres is not so cratered, or is there something that you're missing, or is there more work to be done? I mean, we look at Pluto, several huge craters on Pluto, notably, of course, the heart-shaped feature. So I just wondered, well, what are the theories? Was Ceres just not bombarded, or are we not seeing the evidence?
Okay, great question. Well, we do see a lot of craters on Ceres up to about 100 kilometers in diameter. The population that's smaller than that is what would be expected for a body in Ceres neighborhood. Based on the models of the asteroid flux, which have been developed from cratering records on myriad solar system bodies. So clearly there is a deficit of large craters on Ceres. There are 3 that are fairly large, the Urvara Ulodi in the southern hemisphere, and then the large Kirwan crater closer to the equator. And they clearly have cratering characteristics, the characteristics of a classical impact crater. And then after that, there's really nothing. So we speculate that the properties of the subsurface are such that these larger craters will relax over time. Not that these impacts didn't occur, but that the record of them has been largely erased. There are several cryptobasins, meaning hidden. We kind of can see the outline in a rim topography, and they're very deep excavations, and we've identified 3 of those. And that would be consistent with what we would have expected in terms of the largest impacts hitting Ceres. So the conclusion that was reached by the studies of science team is yes, Ceres it experienced the same impact history as other objects, or that would be expected there. But the surface it's not so much resurfaced as the surface has been modified over time such that you can't recognize those signatures anymore.
In some ways, it's similar to what we were talking about earlier with the Ahuna Mons volcano. Over time, the ground relaxes back to its original shape.
All right. Well, speaking of time, we're going to move on to a look at the end of the mission and what's going to take place. I have a video here that is taken by DLR and our German partners, and it's a view from the 2 lowest orbits, and the final orbit is the orbit that Dawn will be in for decades to come.
And the one before, the orbit before that, was about the same height above Ceres as the International Space Station is above Earth.
All right.
About 240 miles.
Let's take a look. And those are spectacular images. They really
The
are.
lowest ones, we should have clarified, were taken from an altitude of only about 22 miles. It's 3 times higher than you are when you fly cross-country in a commercial aircraft.
And let's talk about that. That is Dawn's final orbit, and we've got the actual view of the ellipse to give people an idea. That is the final orbit that Dawn will be locked in from here on out.
Right, that's the orbit that it's been in since June 9th, and every 27 hours it swoops down to just 22 miles high, and then it flies out, soars up to 2,500 miles, and then comes back down again.
Let's talk about that, how the mission will end. It'll stay in that orbit, but why did we pick that method?
Because, as we discussed earlier, we want to protect Ceres from the terrestrial contamination, the organic materials that are on board the spacecraft. But at the same time, we wanted to get as low as we possibly could in this final phase of the mission to get the highest resolution, the coolest, most spectacular views, and other rich science data that are not pictures, but spectrometry and measurements of nuclear radiation that emanates from Ceres. And so we found this orbit that allowed us to come down to very low altitude about once a day, and yet the orbit would remain relatively stable for decades to come. And so that's why we're leaving it there.
Carol, anything regarding this?
Well, I just wanted to mention, you could see clearly from that animation that this orbit was like putting your glasses on if you don't see very well, and all of a sudden those rich details popping out, and it's really given us a lot to work with and try to understand the geologic processes which are in placing these bright deposits on the surface, and giving us some insights into what kind of plumbing system is going on under the surface. So it's just been just a fabulous end to the mission.
All right, well, we have some social media questions. In fact, we have a lot of social media questions. Here's one from Facebook from Paul Higgins. The Expanse imagines a future in which humans live on Ceres and mine in the asteroid belt for water, ice, and minerals. This is a TV show. Yes. Do you see anything plausible in that?
Well, so I'll mention, I actually haven't seen the TV show, but I've read the novels, which I find very entertaining. I will mention that their depiction of Ceres is entirely different, not at all like the actual Ceres. But I'm sure at some point, as humankind expands farther and farther into the solar system, far in the future, sure, it's credible that people will be there, and because a substantial fraction of Ceres' mass is water ice, it's a resource that future explorers could use at some point. But Ceres is farther than Mars. It's not easy to get to. That's one of the reasons we needed ion propulsion. And so I think that future is pretty far away.
All right, here is a second question. What's the next step for ion propulsion? Jim, do you want to take that first? Next step for ion propulsion.
In fact, right. So indeed, many of our technologists are developing a capability that leverages the same basic physics, the same basic concept, but make it more efficient and make it a larger thrust associated with it. So we've been investing into that for many, many years. And in fact, human exploration is now starting to pick up the idea that indeed, as we go back to the moon and have a system called the Gateway, this will be in what we call cislunar space in the vicinity of the moon and the Earth, enabling us to do all kinds of new research on the moon. That will also have these ion engines. So I think we're just seeing now the start of how they can be applied in many missions. I would like to see more planetary missions have this capability. It's becoming more available.
What do you think, Mark?
I agree with Jim. I mean, the way I think of it is ion propulsion is a tool in the toolbox of mission designers. And so for each mission, the question to ask is, what's the most effective way for NASA to get the science, given the constraints that we have of physics and the responsible use of taxpayer dollars that we're privileged enough to use? I think we'll find many, many future exciting missions destinations that we couldn't otherwise reach, and missions that we couldn't otherwise undertake that will take advantage of ion propulsion.
And we're coming close to the final 10 minutes here. Your thoughts as this mission is coming to a close, your personal feelings about this mission. What are your thoughts? Do you focus on the fact that it's coming to an end, or all the great stuff you got?
Absolutely all the great stuff that we got. We have so much data that we've, I wouldn't say we just scratched the surface, but we really haven't done all of the deep analysis and put things together in comparison with other bodies that we know of in the solar system. And so I'm really looking forward to working on these data, with the community working on these data, and really see how far we can go in understanding that comes from this fabulous mission, which has taken up a large portion of my career. It was selected in the year 2000, and you know, so it's just been a long and awesome journey.
Mark, how about you?
Well, I of course agree with what Carol said. I mean, the spacecraft and the mission are coming to an end, but the advancement of knowledge is going to continue and probably even accelerate as there are more and more analyses applied to the data. But with regard to the mission itself, I mean, as we said in the video and Carol said, it's a part of you. I mean, it's something. It's really exciting to work on a mission that's so far away. I mean, Dawn it's more than 1 million times farther away than the space station, well over 1,000 times farther than the moon, farther than the sun. I think it's really exciting personally to be able to work on that, and I think it should be exciting for everybody. I mean, this is a mission of humankind, as are other interplanetary missions, and I just think it should be exciting for everybody to look up at the night sky and think, gosh, we have spacecraft out there. I think it's really
pretty amazing.
It is really amazing. And when it comes to an end, I'm both sad that it's ending, and yet I couldn't be more thrilled with how successful it's been.
You could not possibly be any more proud of what you accomplished, and when you had adversity, you guys figured a way out of the box to make it still work.
And when you say you guys, it's not us sitting at the table. It's a large team of committed, capable, diligent, passionate, expert engineers and scientists who really worked hard to make this mission successful, and I could not be more proud of them and the opportunity to work with them. It's been a wonderful experience to make this mission a reality.
Well, Jim, do you have anything to add to that?
Oh, yes, I do. Because, you know, as head of planetary for a number of years, I saw the dedication in many planetary teams, and it is absolutely so remarkable. They are so dedicated and they work so hard. They literally, this is really a major element of their life. And these missions are not easy. They're incredibly difficult. Each and every one are special in the way it's put together, the way it is implemented, the science that it obtains. No one spacecraft is identical to the other. I mean, they go to far reaches, from Mercury, where it's so incredibly hot, to Pluto, to where it's so incredibly cold, and all the systems that have to be designed and developed to do that. You just pour your heart out into this, and it's tough when these things end. But the legacy of the mission, of course, is the data, the ability to be able to go back, find new things, new discoveries. And there's many things I know that our scientists have seen, recognized, they can't explain it, and sort of put that in the back of their mind until something else clicks and they can put it together and make other discoveries. This happens throughout our solar system, which makes the planetary community so important to us to continue to fund and work in these areas, find great missions for the next one and next generation to get involved in. But I too will feel sad about Dawn. You know, I watched it launched. I helped it through some tough times from a number of ways financially. You know, I remember the time we were going to launch it, and we kept getting storm after storm after storm. And I had to make the decision, we're going to disassemble the rocket, we're then going to launch Phoenix, and then we're going to put Dawn back on the launch pad. You know, and those kind of things really endear me to being part of that challenge and part of overcoming the major difficulties that occur. And so I have that same feeling, Mark. And I'm with you on that one. And Carol, I know we're going to continue to analyze data, and I'm with you on that one too.
All right. Well, while we have you, Jim, give us an idea of what's coming up for NASA with asteroids.
Well, this is another spectacular time that we are in, for which we have small body missions. And the very next one, OSIRIS-REx, is going to go to another small world. It's an asteroid called Bennu. This particular body is unlike Vesta, unlike Ceres. It's what we believe is a carbonaceous chondrite. It's about 500 meters in size. You know, well, whereas Vesta is 500 kilometers in size. This is much different. But its material is very important for us to be able to return. So the concept is, this is a sample return mission. We will go to Bennu, which we've already started to see. By December, early December, we will be getting into the vicinity to the point where we'll be mapping in high resolution. We'll go down to the surface, acquire material, and then bring that material back, put it in another capsule, and return that capsule to Earth. So not only will we study that object for more than a year, but flying in its vicinity, we'll be acquiring a sample and bringing it back. And what do we expect in this sample? Well, carbonaceous chondrite means it has all kinds of carbon compounds, and perhaps complex carbon compounds, maybe even amino acids. This object, which bombarded the Earth, in particular, these type of objects, after the Earth was formed, perhaps brought ingredients like that to Earth that helped seeded the top layer of the Earth that may have, you know, in some way been used to start life. Another series of questions we want to know about this particular body we'll start to answer. So that's coming up in December. So hang on to your seats. Here comes another small body to investigate.
Well, we'll be looking forward to it in December. That wraps things up for us. Carol, thank you so much. Mark and Jim, you too. If we did not get to your questions, do not fret. Just go ahead. We'll be staying on the line. We will still be answering the Ask NASA questions for another good half hour. In fact, our experts are going to hang around for you. So if you would like to learn more about Dawn, there is a website for you that you can peruse to your heart's content. That is nasa.gov/Dawn. I hope you had a lot of fun. I know we did. Thanks for joining us, and we hope you got your questions answered. Take care.